Let's take a look at example problem 3.3.3, a three-gear system. So in this problem, we have a system shown in the diagram here where we assume that the shaft inertias are small. The remaining inertias are given to us in units of kilograms times meters squared, where I1 is equal to 0.005, I2 is equal to 0.01, I3 is equal to 0.02, I4 is equal to 0.04, and I5 is equal to 0.2. The speed ratios are also given to us as the following. Omega 1 over omega 2 is equal to 3 over 2, and omega 2 over omega 3 is equal to 2. They want us to obtain the equation of motion in terms of our omega 3, and we assume that the torque is given to us as T. So now that we've had the opportunity to look through the problem statement, understand what they've given us and what they're asking us to solve for, the next thing we want to do is create our setup page. Again, our setup page, we redraw a simplified version of our diagram, clearly write out all the given information from the problem statements and what they're asking us to solve for, along with any assumptions that we're going to make. For this problem here, they tell us our torque is T. They give us our I1, I2, I3, I4, and I5. They give us a numeric value, and they tell us the units are in kilograms times meters squared. You can reference back to our diagram. Sometimes for something like this, it might be better to draw it out even bigger if your handwriting is messy like mine, or reference back to the given diagram as well, so we can clearly see, okay, our torque is here. We have this shaft 1, shaft 2 there, and shaft 3 there. We have our inertias and our omegas associated with shaft 1, associated with shaft 2, and those associated with shaft 3 there, so we can understand what's going on. They also gave us these speed ratios. Omega 1 over omega 2 is equal to 3 halves, and omega 2 over omega 3 is equal to 2, where they want us to solve for everything in terms of omega 3, specifically find our equations of motion. So this is going to relate our omega 1s and omega 2s in terms of our omega 3 in order to solve for that equation of motion in terms of that omega 3. We assume the shaft inertias are going to be small, which is given in the problem statement. So now that we've got our setup page created, we have a spot that we can go back to reference all of our given information, diagram, and what they're asking us to solve for, we can begin our solution now. So what I want to start with for our solution is to take a look at these speed ratios that they gave us in the problem statement. We know we need our final answer for our equation of motion in terms of our omega 3, and they give us these ratios that relate our omega 1, omega 2, and omega 3, which relate to our shaft 1, shaft 2, and shaft 3. So let's rearrange those so we can get omega 2 in terms of omega 3 and omega 1 in terms of omega 3, so we can sub those into our equation of motion at the end. So I start off with my relationship here that we have omega 1 over omega 2 is equal to 3 over 2. I can cross multiply and say omega 1 times omega 2 is equal to omega 2. Sorry, omega 1 times 2 is equal to omega 2 times 3, so that gives me 2 omega 1 is equal to 3 omega 2. If I can rearrange that, solve for omega 1, my omega 1 is equal to 3 halves omega 2. But now I also know for my omega 2, I can take this relationship over here where I have omega 2 over omega 3 is equal to 2, solve that for my omega 2, and omega 2 is equal to 2 times omega 3. I can plug that into this relationship here, end up with omega 1 is equal to 3 halves times 2 times omega 3. Eliminate the 2's there, they cancel out. So now I have an expression that omega 1 is equal to 3 times omega 3. So there is my relationship between omega 1 in terms of omega 3. Now I already have from this here, omega 2 is equal to 2 times omega 3, so that's how I relate. Anytime I have omega 2, I can sub in 2 times omega 3. So now I have relationships for omega 1 and omega 2 in terms of omega 3. So that's how we can get everything in terms of that. We're told now that our torque is given to us as T. So the torque on shaft 3 is going to be due to T, which is going to be 1/3 T of our given torque. So the next step in our solution, start solving for our kinetic energies. So we recall our general equation for kinetic energy. So we have Ke is equal to 1/2 I omega squared. Now what I want to do here, as I mentioned earlier, is sometimes these given diagrams are very complicated. A lot of moving parts to it, and drawing it by hand sometimes might not make it clearer to follow. So this is definitely the case here, especially if you don't have most perfect penmanship. maybe stick with the diagram that's given to you in the problem statement. So I've done that here. I've just copied this over and used this as my sheet as part of my solution here. So I can see I have a shaft 1 up here, shaft 2 here, and shaft 3 down here, where my shaft 1 is going to have my omega 1, I1, and I4 associated with it. And that's where our torque is applied up here. My shaft 2, I'm going to have my omega 2 and my I2 associated with shaft 2. And for shaft 3, I have my I3, omega 3, and I5. I wrote that out very clearly for each of those, shaft 1, shaft 2, and shaft 3. Now for each of these, I need to come up with my kinetic energy relationship here. So my total kinetic energy is going to be the kinetic energy from 1, 2, and 3 all combined together. So I write these out, but I kind of write them out in separate lines, make it a little easier for myself. So kinetic energy when I'm dealing with shaft 1 is 1/2 I4 omega 1 squared plus 1/2 I1 omega 2 squared, because those are the two things that are associated with shaft 1 there. 2, we have 1/2 I2 plus my omega 2 squared. There's my I2 and my omega 2 squared. Second one here. 3, dealing with this down here. Now I have my 1/2 I3 omega 3 squared plus 1/2 I5 omega 3 squared there associated with that. Combining those all together, adding them up, that is my equation for my kinetic energy. Now within that I can reduce and simplify. Do that here. My kinetic energy equation now becomes 1/2. Combine my i's there, pull up my omega 1 squared, I4 plus I1 times omega 1 squared, plus I2, 1/2 I2 omega 2 squared, plus 1/2, pull up my omega 3 squared here, is I3 plus I5 times omega 3 squared. Now, this is where I wanted to solve for my equation of motion in terms of omega 3 only, so I need to eliminate my omega 1 and omega 2, but I've already done that based upon those ratios they gave us in the problem statement. So I know that omega 1 is equal to 3 omega 3 and omega 2 is equal to 2 omega 3. So I can plug those relationships right in for omega 1 and omega 2, giving me my entire kinetic energy equation here in terms of only my omega 3. So once I plug in those ratios for omega 3 into my kinetic energy equation, here's what I end up with now. Kinetic energy is equal to 1/2 I4 plus I1 times now 3 times my omega 3 squared, plus 1/2 I2 times 2 times my omega 3 squared, plus 1/2 I3 plus I5 plus my omega 3 squared there, where I have numeric values for all of these values for I1 through I5 that are given to me in the problem statement, and I can reference back to them on my first setup page. My units are in kilograms per meter squared. So I can take each of these. I1 is equal to 0.005, I2 is equal to 0.01, I3 is equal to 0.02, I4 is equal to 0.03, and I5 is equal to 0.2. And plug those in where they belong into that equation for my kinetic energy. I do that there, and I end up with this relationship here once I plug in for all of my I terms with those numeric values there. From that, I can combine them, simplify. It comes down here now to my kinetic energy is equal to 1/2 0.405 times omega 3 squared plus 1/2 0.04 times omega 3 squared plus 1/2 0.22 times omega 3 squared. Combine these all together now, and what I end up with, so you can see there's an omega 3 squared on each of those. Kinetic energy is equal to 1/2, sum these all together, 0.665 times my omega 3 squared. Or if I go back to my general equation for kinetic energy is equal to 1/2 I times omega 3 squared. So my value for I, for my shaft 3 on the output there, is going to be equal to that value of 0.665. So the speed is reduced by a factor of 3 from shaft 1 to shaft 3, and the torque is going to be increased by a factor of 3. So as we're solving through some of these problems that have multiple steps along the way to get to our final solution, it's great to reference back to our first setup page where we know exactly what we're looking for as our final answer for the problem. In this case here, they'd ask us to solve for the equation of motion relative to our omega 3. So the next thing we're going to need in order to do that is our governing equation for equation of motion for angular motion. So we recall that that's equal to T times I alpha, or T is equal to I times my omega dot here. So then we can start plugging in for this. So we know for our torque over here, we found for shaft 3 that our torque is going to be 3T. This is equal to the right side of the equation, I times omega dot, where we're dealing with omega 3 here. We can plug that in. And now our I we just solved for on the previous page here, our I is equal to 0.665 for shaft 3 there. Plug that all in, what we end up with is 3t is equal to 0.665 omega 3 dot as our equation of motion. That's exactly what they asked us to do, solve for it in terms of omega 3.